Thank you so much and welcome to Mr. X free online class for acids and bases. My name is Kolani, popularly known as Mr. X. I welcome you and thank you for coming on time. We're going to have a great time today as we learn quite a lot. So who am I? I am a physical sciences and mathematics science and mathematics tutor who specializes in grade 10 to grade 12. I tutor, I teach, and I've got a great pass rate with over 80% of my students achieving great marks. So definitely you're in the right hands. Today's lesson is free and I am interested in talking about acids and bases. And all we're doing is questions only. Right? I tutor on a one-on-one basis or on group classes. Group classes would look something like what you guys are at right now, which is a meeting on Zoom where we're all learning as a group. It's going to be an exciting time as we do acids and bases. Now, there's more to this. I also do weekly lessons online with groups of students, and these are the lessons that I'm going to be having. So tomorrow, the 17th of August, I'm going to be doing physical sciences, electric circuits part 1. Sunday, the 20th of August, I'm going to be doing analytical geometry. So it's quite interesting what we're going to have. Very affordable, quality and affordability with Mr. X. You're looking at 100 rands for a 2-hour session. So if you would like to, these are the contacts: 073-974-8498. You can also find me on Instagram under the handle Mr. X Med Science. My YouTube channel where I'm going to be uploading this particular lesson is Mr. X Mathematics and Physical Sciences for grade 12s right there. Very interesting right there. So I offer all of that. But I've got something bigger than what you guys have ever seen. I'm doing a massive 3-day revision program that's going to take place in Damelin College in Braamfontein. I've put the address right there. What it means in this 3-day revision program is that it starts at 8 o'clock in the morning until 4 p.m. with only 15 minutes break. Massive revision, question after question, paper 1, paper 2 questions for full 3 days with me. Most of you guys are used to having me for like 2-3 hours, but now you're going to have me 8 hours a day. That's 8 full hours a day for 3 days, face to face. And this one will be 1,000 rands per subject for 3 days. So it's a game changer. Book now. So booking is free. Just text me. I'd like to book for this. You specify I want to do maths, physics, or maths only, or physics only. Then I book for you. Then your payment will secure your space. I'll tell you this. I think I have over 100 people that have booked. And so there's still space a bit. Some of them I know will fall off, but then booking is free. So hurry while space lasts and limited space is available. Now, having said that, just want to show you a snippet of what happened in the program of 2022. What happened? So we were having a bit of some fun with my students. In 2022, these are the people that I was teaching at the Mr. X massive revision program. You can see the many students. And let me tell you, these students are at varsity doing their advanced degrees. They're doing well. They learned. It was a massive game changer. This is them right here, 2022. 2023 will be bigger, better, massive. And this is the man, Mr. X, doing his thing that he loves, passionate about, as he teaches the children. As you can see again, that's what's happening. All right, perfect. Now, that having been said, I want us to start on our lesson. What I'm going to do is I'm going to deactivate my video right now. So you're going to be hearing me, but not seeing me. Get your pens ready. Ensure that all your videos are off. Let's get the right attitude. It's about 7:10. We'll end our lesson at 9:15 so that at least we are guaranteed. All right, fam. I am ready and let's do this. All right. So, yebo, let's do this. Avoid writing on my screen, please. Avoid writing anything on my particular screen. So here's the first question that we're going to start with right here. It's a 2014 prelim paper. It's paper 2 and it's question number 8. And it's a Mpumalanga paper. Maybe you can write down the title and then I can start off. So I'll do calculations. I will do definitions. I will do a lot of things. So as we go along, you let me know what you don't understand, and so goes the story. If I was to tell you anything about this particular topic, I will tell you that you would need to listen, read properly so that you can fully understand. All right, I'm ready. It says to me on this question, ethanoic acid is a monoprotic acid. So they gave me the formula. Ethanoic acid is a monoprotic acid. Then 8.11 says, what is meant by the term monoprotic acid? I want to advise you that definitions are 2 marks or 0. In other words, any one of you will get full 2 marks or will get nothing when it comes to definitions. So when you are dealing with this particular topic and it says define or what is meant by the term monoprotic acid, the answer would be monoprotic acid, write the following. A monoprotic acid is an acid that can donate. A monoprotic acid is an acid that can donate only 1 proton per molecule. Is an acid that can donate only 1 proton per molecule. That's a monoprotic acid. All right, so only 1 proton per molecule. So it would mean that if I dealt with a diprotic, it would mean 2. Di means 2 protons per molecule. If I dealt with the triprotic, it would be 3 protons per molecule. So the definition is done. An acid that can donate 1 proton per molecule of acid. 8.12. When ethanoic acid is mixed with water, ions form. Give the chemical formula of the ions that form. So here's the story. You've got ethanoic acid, and the question says when you react it with water, so this will be ethanoic acid in solution or in water, and it says that ions will form, and they want the chemical formula of these ions. Be clear that ethanoic acid is the one which is acting as the proton donor, because when you define an acid is a proton donor. Water, on the other hand, will decide to be the base which accepts that particular proton. So when you have the acid donating the proton, notice that your ions will be the following: H3O+. So the water will accept an ion and form the hydronium ion. So this is called hydronium. So the water accepts that particular H+ and then forms the hydronium ion. In this case, the ethanoic acid, because it lost an H, it then forms the ethanoate ion. So this is the ion that is formed, the ethanoate ion. Let's go back to this. So I need you to understand what really goes on here. You've got the acid, which will donate the proton. Water will accept the proton. And then instead of 2 H's, as you can see, you now have 3 H's, which is the hydronium ion. Then because the acid donated the proton, lost the H+, it becomes the ethanoate ion with the minus. So somebody may be asking themselves, so how would I know this? Now, when you accept a proton, you are going to be, at the end of the day, when you accept a proton, you're going to become a plus. So every time you accept a proton, you become a plus. When you lose or donate a proton, you become a minus. So that's how you'd know this. When I teach you the topic electrochemistry, or when we revise the topic electrochemistry, you'll be able to see all of this. So in terms of the formula, we are looking at this and that in answer to 8.12, the H3O+ and the CH3COO- ion. 8.13, we're just still dealing with the theory. We've not done any question of calculation, so the theory is very important. The story begins like this on 8.13. It says to me, a solution of ethanoic acid, which is this formula, of concentration, 1 mole per decimeter cubed, conducts electricity, but not as readily as a solution of hydrochloric acid of the same concentration. Give a brief explanation for this observation. Now, I want you to understand, and you'll go back to lessons on acids and bases. Acids and bases are conductors of electricity. Acids and bases are good conductors of electricity. Now, the electrical conductivity of an acid or a base depends on 2 things. Number 1, it depends on the strength of that particular acid. So the strength of the acid will give an indication of the conductivity of that acid. And by that way, I would say to you, the stronger the acid, the greater its conductivity. So strength affects the conductivity of electricity of an acid. Number 2, we have the concentration, which I'll put in square brackets, the symbol for concentration. Concentrated acids are good conductors of electricity. So 2 things are essential when dealing with the strength, or rather with conductivity. You say strength of an acid will affect how good conductivity of that acid is, as well as the concentration. In my story, I've got 2 acids, ethanoic acid, I've got hydrochloric acid, and they have the same concentration, which is 1 mole per decimeter cubed. The question says, a solution of ethanoic acid conducts electricity, but not as readily as a solution of hydrochloric acid of the same concentration. So what it means is this. Now, the hydrochloric acid conducts better than the ethanoic acid. And the question is, give a brief explanation for this observation. So let me see what's happening. In terms of concentration, checklist is the same. So the factor that must differentiate them is strength of an acid. Now, if you were to go back to your notes and every other thing, you will notice that hydrochloric acid is a strong acid, while ethanoic acid is a weak acid. And so that explains why hydrochloric acid will conduct better than ethanoic acid, or why ethanoic acid does not conduct as readily. So to do it into a chemistry proper answer, here's what I would say. Write the following. Hydrochloric acid is a strong acid. Hydrochloric acid is a strong acid which ionizes completely, in solution. Hydrochloric acid is a strong acid which ionizes completely in solution to form a high concentration, of hydronium ions. Hydrochloric acid is a strong acid which ionizes completely in solution to form a high concentration of hydronium ions. While ethanoic acid partially ionizes, and has less hydronium ions in solution. While ethanoic acid partially ionizes and has less hydronium ions in solution. All right, fam, good for us. Let's go further. I'm ready for my next one. Okay, calculations, here they come, which is what is the business of the day. The story we read, we understand, we mark the important numbers, we note the names, we go further. 8.2. A standard solution of sodium hydroxide is prepared by dissolving exactly 2.5 grams of sodium hydroxide in enough water to form a 500 cubic centimeter solution. Let's visualize the situation. So you've got your container, could be a conical flask or whatsoever. In it, you put 2.5 grams, 2.5 grams of sodium hydroxide, NaOH as the formula. And then in that one, you add water to the tune of 500 cubic centimeters. So in other words, the solution or the volume is actually 500 cubic centimeters. I want to note that volume is not measured in cubic centimeters, but in cubic deci. So you need to divide this 500 by 1,000. Be very careful about that. So that gives me 0.5 cubic decimeters. That's my situation. 8.21 for 3 marks. Calculate the concentration of the solution. I want you to understand that your choice of the equation will always depend on the information given. What equation you ultimately choose will depend on the information given. And I'm choosing an equation right now. C, concentration is equal to the mass of that substance divided by the molar mass multiplied by the volume. You will find this formula in the formula sheet. Again, your choice of the equation depends on the information that you've been given. All right, let's do the math. C, that's what I'm looking for. The mass 2.5 over the molar mass. Now the molar mass M is found from the periodic table. So you would need to have your periodic table close by, but if you don't worry, I got your back. You will be able to know this when you look at the periodic table. So here's how you'd look at it. Now sodium is 23 in terms of its molar mass. Then oxygen is 16 right there. And then on the flip side, you've got hydrogen, which is 1. And when you do your maths and add them together, they give you a molar mass of 40. 40, and the volume will be 0.5 converted to cubic decimeters. Calculator, and your answer is 0.125 moles per decimeter cubed. That is the concentration of sodium hydroxide. I'm ready for 8.22. You let me know where there's a struggle. Let's do this. We're learning, we're pulling through. All right. All right, let me see what other questions people are saying. All right. Right, somebody says, will it be wrong if I write the ion formed by ethanoic acid as CH2COO minus? Yes, it will be wrong. The H that goes out is the one at the end, not the one that is amongst the H3s. So definitely you write the one that I've just given to you. But thank you for that particular one. Just to reiterate this question that I've just done, your choice of the equation depends on the information that has been given. And I want to say again, concentration is the mass of the object, right? Or mass of the sodium hydroxide, which is 2.5, divided by the molar mass multiplied by the volume. I say this because this formula is available in the formula sheet, and your choice of the equation depends on the information that has been given. Do I have mass? Checklist, yes. Do I have molar mass from the periodic table? I gave it as 40. Do I have volume? Yes, measured in cubic decimeters. So we divided cubic centimeters by 1,000. So you got 0.5 cubic deci. And at the end of the day, 0.125. I'm ready for 8.22. Story, here we go. 20 cubic centimeters of this solution of sodium hydroxide is titrated. There's a key word there, is titrated with ethanoic acid. Sure. The volume of the acid required for the titration is 24.5. Calculate the concentration of the acid, and they gave us the chemical equation, another 3 marks. Follow my line of thinking. Now, mostly when you deal with the titration, you've got a base are reacting with an acid at certain volumes and certain concentrations. Now, we're given information that 20 cubic centimeters of this solution of sodium hydroxide, 20 cubic centimeters. So the volume of the base is 20 by 10 to the power negative 3. What are you doing, say? When I say by 10 to the power negative 3, I am changing cubic centimeters into decimeters. It's as good as dividing by 1,000. So this 20 cubic centimeters has been changed into cubic decimeters. This is of sodium hydroxide, so that's why I said VB, volume of base. It is titrated with ethanoic acid, and we're told that what we require there is 24.5 cubic centimeters of the acid in order to neutralize. 24, let me read that again, 24.5 by 10 to the power negative 3 cubic decimeters. The question says, calculate the concentration of the acid. Ca, I'm looking for Ca. Now notice that I do have Cb. Ca is concentration of acid, Cb is concentration of the base. So when it comes to the concentration of the base that we're using is the sodium hydroxide, whose concentration we found previously as 0.125 moles per decimeter cubed. Be very careful about that situation. So I've gathered my information, and my story says your choice of the equation depends on the information given. Ca, Va, Cb, Vb is equal to Na over Nb. That's the choice of the equation. In that aspect, here's my story. Ca, concentration of acid, I don't know you. Va, that's my 20 by 10 to the power negative 3. Cb, 0.125 multiplied by Vb, which is, the Va should be the 24. I think I made a mistake. Yes. Sorry about that. 24.5 by 10 to the power negative 3. And the Vb is the one which is 20 by 10 to the power negative 3. All this is equal to Na. And if you compare it to my first lesson, and by the way, I did this first lesson, then the theory when I was teaching from scratch. I've done it with my online classes, but they pay for that. Remember I said I also do those classes that I paid for. They paid for that one. This one is free. It's 100 rands. And I always record all my videos. So just in case you struggle with this one and you'd like to have that one which is recorded, holla at me. It's 100 rands for that particular video, and it remains with you forever. So Na, number of moles of the acid from the balanced equation. So I come here to the balanced equation. Number of moles of the acid. So if I look at this, the ratio is 1:1. 1 mole of acid right there. So I'll put the 1 over 1 mole of base because the ratio is 1:1 right there. So the Na and Nb are the number of moles of acid and base from the balanced equation. The rest is mathematics. Let's do some maths. So here I've got Ca times 24.5. Let me just get some space here on this one. Let me get this a bit closer. All right, so this is equal to 1/1. And then I'm going to get this a bit closer. So Ca times 24.5 by 10 to the power negative 3 would be equal to, I'm going to cross multiply, 0.125 by 10 to the power 0.125 times 20 by 10 to the power negative 3. And so to find your Ca, it's just basically going to be 0.125 times 20 by 10 to the power negative 3. You got your calculators over 24.5 by 10 to the power negative 3. To get your answer, it's 0.102 moles per decimeter cubed. That's your answer for that one. Please write it down. Right, we're ready. We're learning. or pushing through. You let me know where there's a struggle, where you don't understand. All right, 8.23, 8.23, a bit of some theory on 8.23. Okay, let me try 8.23 with you just to teach you something. And don't forget what I'm going to show you now. I'm about to take this out, but I want to concentrate on 8.23. The question is quite clear. Which is the preferred reactant that should be placed in the burette? Then it says, explain the answer for 2 marks. Now, when these questions come, the examiners assume that you have done the experiment on titration using sodium hydroxide with ethanoic acid or sodium hydroxide with another acid. Now, the question says, which one is the preferred reactant that should be placed in the burette? Let me jog your mind a bit. Now, the burette is basically a piece of apparatus whereby, when I taught you guys on part 1 of this topic, I said in the burette, you put your standard solution. And if you go to the question, they said the standard solution is sodium hydroxide. That's what they said. But then the question says, so which one is the preferred reactant? Now, I want you to understand the basic lab procedure. The problem with putting sodium hydroxide inside here, the burette is open, number 1. And because it is open, if the sodium hydroxide is allowed to stand for longer periods of time, it evaporates and leaves solid sodium hydroxide. And so when the solid sodium hydroxide is here, this tap will not be able to turn. Let me go back to this. While I've always said that the standard solution should be in the burette, I want you to know ultimately that in this case, when you put the standard solution is sodium hydroxide into the burette, the problem is that if it evaporates or is allowed to stand for longer periods, it leaves or it solidifies, and then the tap will not be able to open due to the solid formed due to the evaporation of the sodium hydroxide. Same way when you would, for example, if you take salt and water, and then the salt dissolves in that particular water, right? When you dissolve, or rather when you evaporate the water, there's a solid, the salt remains. So what is essential here is to understand the experimental procedure from the perspective that if you were to add sodium hydroxide into the burette, definitely it will solidify. So 8.23, which one is the preferred reactant? The answer, it is the acid. Then I need to explain that with what I've just said. Right, the following, it is the acid. And why can't we put sodium hydroxide? Answer, when sodium hydroxide is allowed to stand for longer periods, when sodium hydroxide is allowed to stand for longer periods, when sodium hydroxide is allowed to stand for longer periods, it may evaporate. It may evaporate, leaving solid, leaving solid, leaving solid sodium hydroxide, leaving solid sodium hydroxide, and the tap will eventually not be able to turn, leaving solid sodium hydroxide, and the tap eventually will not be able to turn. And the tap will eventually not be able to turn. All right, just want to get some more info onto this and all. So it says to me, it's the acid, right? So I prefer the acid. That's what I prefer, the acid. And then because when sodium hydroxide is allowed to stand for longer periods, it may evaporate, leaving solid sodium hydroxide, and the tap will not be able to turn. Right, let me just answer a couple of questions that I see popping up here quickly. All right, let me see the first one. Somebody says, so the acid is always the preferred one to be placed in the burette. No, in this case, yes. Because I'm dealing with sodium hydroxide, definitely, I require the acid to be in the burette. Otherwise, as I just said, it will evaporate and solidify. Then somebody says to me again, what do you mean the standard solution is always in the burette? When you're doing the experiment of titration, the standard solution goes to the burette. Those are the standard procedures. It always goes to the burette, except in this case, whereby, again, it will solidify. So it's always in the burette. Let me go further. 8.24. The table below shows some indicators and their pH ranges. 1, 2, 3. Select a suitable indicator for this titration and give a reason for the answer. All right, let's work it out together. Now, sodium hydroxide is a strong base and ethanoic acid is a weak acid. Now, the solution that is formed eventually is going to be basic. It's going to be basic. And somebody is asking, how would I know that? The key is strong base. So when you're reacting a strong base and a weak acid in a titration, your ultimate solution that you're going to form is going to be basic, because strong base, the key word is strong base. So it's basic. And so when you have a solution which is basic, your preferred indicator must be an indicator which can work on basic pHs. When I say basic pHs, I'm talking about pH that is greater than 7, right? Greater than 8 to be even more specific. And so when I look at this, the one that is preferred is phenolphthalein. That would be how you pronounce it. Phenolphthalein. Why say? Because it has an equivalence point. That's the chemistry. It has an equivalence point of greater than 7 because my solution is basic. So I need an indicator with a typical pH range greater than 7. So the answer is phenolphthalein. And they said, give a reason for the answer. I just want to reiterate this. Try to write as quickly as possible. I really want to do quite a lot of things. Right, here's my answer, phenolphthalein. Hope you've written that. And then here's what we say. A strong base and a weak acid. A strong base and a weak acid titrated. A strong base and a weak acid titrated. A strong base and a weak acid titrated will form a basic solution. Will form a basic solution. Will form a basic solution. Full stop. Will form a basic solution. Full stop. Then you say the equivalence point of the indicator, must therefore be basic. The equivalence point of the indicator must therefore be basic. All right. So when I say equivalence point, I'm saying the point where the titration would have its end point, and it's going to be on the basic side since I'm dealing with strong base and weak acid. So the equivalence point definitely must be greater than 7. All right, let's do more. My next one here, right? The following is the 2015 Northwest paper. I want to show you a couple of things. It's a very interesting question. So I really want to do more of the calculations more than anything else. All right, 2015 Northwest prelim paper 2, and it's question number 5. Let's do this one together. Write down the title, the page number. There's a couple of things I want to teach you here. 5.1 is always your basic questions and all. So if you're using a phone, fam, you can always zoom in, zoom out in case you can't see a question or a number. Zoom in, zoom out as much as you want, right? If you're using a laptop, it's even better because it's a bigger screen. Define an acid in terms of the Lowry-Bronsted theory. For 2 marks, you would say an acid is a proton donor. An acid is a proton donor. An acid is a proton donor. All right, good. Then it says, consider the reaction below. So you've got that reaction. It says, identify the reactant which acts as a Bronsted-Lowry base. Identify the reactant which acts as a Bronsted-Lowry base. So the base must be the one that accepts. Let's look at the equation. HF plus H2O, and let's see the before and the after. So if I look at H2O, there were 2 hydrogens before, and now there are 3. This guy must have accepted. So he is the base. So remember, the base is the one that accepts. And if you contrast it, if you look at HF, and you look at F minus, so this guy must have donated. This is why he has lost that H and has become F minus. Let me just write it a bit more here. So you got HF plus the water, and it's going to give you the H3O plus and the F minus. Now, again, the water will act as the base, HF as the acid. HF gives to the water, and then we have H3O plus F minus. That's your answer. So it says identify the reactant. The answer is H2O. So write it down, H2O for 5.21. 5.22, here we go. 5.22, here we go. Says to me, write down the formula of the conjugate acid of the base identified in question 5.21. Write down the formula of the conjugate acid of the base identified in question 5.21. Sharp. Let's enter them. Whenever a base accepts a proton, it forms a conjugate acid. I say that again. Whenever a base accepts a proton, it forms a conjugate acid. So the base is water. When it accepts a proton, it's going to form a conjugate acid, which is this one, which is known as the hydronium ion. So the question says, write down the formula of the conjugate acid, this one, of the base identified. The base was water identified. When it accepts a proton, it forms a conjugate acid. And on the same note, let me stretch this further. When an acid donates a proton, it forms a conjugate base. So the F minus ion would be your conjugate base, right? So in this case, I want you to understand that when a base accepts a proton, it forms a conjugate acid. When an acid accepts or rather donates a proton, it forms a conjugate base. Just to clarify, the answer to this one, 5.22, would be this, H3O plus, because they talked about the base and they want the conjugate acid of that base. Thank you. 5.3, I'm ready. 5.3 says, sulfuric acid is a strong acid. Okay, thank you. 5.31 says, explain why sulfuric acid is considered a strong acid. And so my answer would be, because it ionizes completely in water, ionizes completely in water, ionizes completely in water, to form a high concentration of hydronium ions. Ionizes completely in water to form a high concentration of hydronium ions. To form a high concentration of hydronium ions. A high concentration of hydronium ions. All right, 5.32, here we go. Calculate the pH of 0,025 mole per decimeter cubed sulfuric acid solution. That's okay. I don't know if people can still hear me. Can people hear me? All right, perfect. All right, I think we should be okay. I think there was a bit of a glitch on my side. Not so sure what happened. I'd like to apologize for that, but the show continues. The question says, calculate the pH of 0,025 moles of sulfuric acid solution. Now, I want us to think together and we pull through from here. The concentration of sulfuric acid is given as 0,025 moles per decimeter cubed. Okay, cool. And we're looking for the pH of that acid. Now, first thing is first, sulfuric acid is a strong acid, so I'm expecting that its pH should be less than 7, maybe even closer to 2 to 1, because the lower the pH, the stronger the acid. Now, in terms of how sulfuric acid ionizes, when sulfuric acid dissociates in solution, it forms this structure of 2H plus, is diprotic, plus the sulfate ion, like this. So that's how it actually forms it. And so because of that, when you're calculating the pH of a diprotic acid, be very careful. And why I'm saying this is because pH normally is negative log concentration of the hydrogen ions, or you can say hydronium. So you're still allowed to write it like this, the hydronium ions, whichever you use, it's fine. Remember, they are interchangeably. So how then do I deal with the pH of a diprotic? I want you to understand, and here's the key to this answer. I want you to understand that when dealing with the diprotic acid, the concentration of the hydrogen ions or hydronium ions is always twice the concentration of that particular acid or diprotic. Oh, listen to this very carefully. So when dealing with the diprotic, excuse me, when dealing with the diprotic, the concentration of that H plus is twice the concentration of the diprotic acid. If it was monoprotic, mono like HCl, then the concentration of the H plus would just be equal to the concentration of the HCl. If it was triprotic, the concentration of the H plus would be 3 times the concentration of that triprotic acid. So please do not forget this at any particular point. It's diprotic, so the concentration of the H plus, the ratio is a 2:1 situation. The concentration of the H plus is twice the concentration of that particular sulfuric acid. So to answer our question, pH would be negative log. What is the concentration of H plus? Twice that one of the sulfuric, 0.025. So your answer at the end of the day is 1,3. And pH does not have units, right? Does not have units. Okay, somebody's asking, say what happened to the negative log after I changed it. Let me see, what did you say? After you changed it to, I can't see the rest of the question, eh? Twice as much. I can't see that. Maybe you can just raise your hand and help me out with the just saying what you need to say. So I'm on 5.31, 5.32. I've answered that. And you let me know where there's a struggle. But for me, this is quite key that when you're dealing with this solution, ensure that is diprotic, you multiply the H plus, or the concentration of the H plus will be twice as much. Right. I'm ready for the next one. You can reiterate your question again so I can know how to answer properly. Going. Also, says to me, a certain solution X has a pH of 12,8. So the pH of solution X is 12,8. Thank you. Which ions, or H minus or H plus, are in excess? So obviously, if it's a pH of 12,8, it's a pH which is greater than 7. Anything greater than 7, you're talking about bases. And in bases, the predominant ion is the hydroxide ion. So to answer the question, it is hydroxide. These are the ions that are in excess. If it was an acid, the pH would be less than 7, and the predominant ions that are in excess would be the H plus. But because it's greater than 7, it's 12.8, we're talking about OH minus. So to answer 5,41, OH minus. 5.42, we read 1 mark again. 5.42, acetic acid, there's acetic acid, is added to solution X. So let's visualize. There's my solution. It's solution X. What are we adding to solution X? We're adding ethanoic, acetic acid rather, which is also ethanoic acid, by the way. Right, so you're adding the acetic acid, the ethanoic acid. Right, is the pH of the solution going to increase, decrease, or remain the same? So you're reacting an acid and a base. So the base and the acid are being reacted. So obviously, neutralization will take place, and the pH, which initially was 12,8, will decrease. So the pH becomes smaller, it decreases. Remember this. When you neutralize, pH is around 7, 8, 7, blah, 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 thereabout. So obviously you're coming from 12,8 and now you're in your pH of neutralization. So you're dealing with the situation where you have it at a pH which is lower than what you had initially. 12,8 was our first one, but now that we added an acid, neutralized, the pH answer will decrease. All right, keep that in mind. Let's keep working. I'm going to my next question. I want the calculation. I just want the calculation. Somebody's got a hand up. There we are. Let's go.
Hi, sir.
Hi.
On the question that you just did, where you said the pH will decrease, I wanted to ask that, isn't that when acetic acid when acetic acid is added, because it's a very weak acid and it doesn't really want to react. So when it's added in water, isn't that it produces OH minus?
All right. So you're saying to me the argument is on the weakness of acetic acid, and that because it's weak and it reacts with the base, it's not going to do much to the base. All right. So here's my argument. The reaction will take place. We can't say it doesn't do anything. It does. That's why it can neutralize it. That's why it's used in titration. So because of that, I understand the idea of the fact that you're saying the solution X is a strong base, pH of 12.8, and ethanoic acid, acetic acid is a weak acid. The solution will eventually be basic, but it's going to be basic at a pH less than the 12.8. It can't go further than that. It can only down. It will be basic eventually, the solution. But then the question was, will the pH increase or decrease? Adding a weak acid, whether it's weak or strong, or to a base, will always decrease the pH, because the pH of a base is lagging at about 12.8, and that one acid comes in and lowers it, or rather decreases it. This is to respect the idea that acids and bases are substances which neutralize one another. So in a high pH, it will definitely lower it down. So that would be the answer to that particular case. All right.
So hydrolysis has not been considered.
All right. Thank you so much. Appreciate. Okay. I'm ready for my next one. The next one says, Elena accidentally spills 15 cubic centimeters of 0.4 sulfuric acid. So let me collect my information. So the volume of the acid that was spilled is 15 by 10 to the power negative 3. The concentration of that acid is 0.4 by 10. All right, it's just 0.4, nothing else. Yeah, 0.4 moles per decimeter cubed. Then it says he adds 25 cubic centimeters of 0.2 sodium hydroxide to the spilled acid. So the base, its volume that is going to add because of the spill is 25 by 10 to the power negative 3. The concentration of that base is basically 0.2 moles per decimeter cubed, just like here, moles per decimeter cubed. The reaction is 1 mole of sulfuric acid reacts with 2 moles of the sodium hydroxide to give you the salt, sodium sulfate, and 2 moles of water. The question says, show by calculations that the addition of sodium hydroxide will not neutralize the sulfuric acid spill. Let's do some logic. Work with me. So your situation is that you have sulfuric acid, which has spilled on a lab, and you want to neutralize. Okay, sharp. So I've got the sulfuric acid there, and I want to neutralize it with the sodium hydroxide, okay? So let me just write them in terms of their formulas. So sulfuric acid that has been spilled, sodium hydroxide. The question says, show that the addition of sodium hydroxide will not neutralize the sulfuric acid spill. Let's do English. The question is telling us to show that sodium hydroxide is not going to be enough to neutralize this acid. The question is telling us to confirm that sodium hydroxide is not in proper stoichiometric values to eventually neutralize this acid. You have not put enough of sodium hydroxide. Show that it's not enough. So here's how you do it. My information is volume, concentration, volume, concentration. I have everything, VACA, VBCB, and I know I have been told that show that sodium hydroxide is not enough. Sharp. Where do I start? My language is always moles. My language is moles. Get the number of moles of the acid that you spilled. So let's convert it into moles. Concentration times volume. Where am I taking it from? The formula that says concentration is number of moles over volume. So in this case, the number of moles of the acid will be concentration, which is 0,4. The volume is 15 by 10 to the power negative 3. And at the end of the day, it's going to be 6 by 10 to the power negative 3 moles. So say, what's this? These are the moles of acid that was spilled. These are the moles that sodium hydroxide is not able to actually deal with. Let me get the moles of the base just to confer, and then concentration times volume again. Concentration of the base is 0,2. The volume goes to 25 by 10 to the power negative 3. Eventually, the base moles is 5 by 10 to the power negative 3 moles. Now, at first glance, someone may say, I can see you require 6, but you have fit. Someone would say, I have 6 moles that I need to deal with, but the base is only giving 5. At first glance, that's what you would think, but that's not how you do it. You see, from the balanced equation, right? I want you to understand what happens here. From the balanced equation, you will notice that sulfuric acid and sodium hydroxide are reacting in the ratio of 1:2. So I want to understand that when I have 6 moles of sodium of the acid, when I have 6 by 10 to the power negative 3 moles of the acid, how many moles of the base would I require to deal with 6 by 10 to the power negative 3 moles of the acid? That's the first thing I need to think about. Because remember, the question has given me the indication that sodium hydroxide is not enough. It will not neutralize the sulfuric acid. How many moles of sulfuric acid do I need neutralized? I need 6 moles of sulfuric acid to be neutralized. And then how many moles of base do I require according to the ratio? 1:2. Let's do the math. You cross multiply 1x, so that's x, 2 times this. I require 12 by 10 to the power 3 moles of sodium hydroxide in order to neutralize the sulfuric acid. Then I need to ask myself, I require 12 by 10 to the power negative 3. How many moles of the base do I have? 5. How much is needed to deal with this sulfuric acid? 12. How much do I have? 5. How much is needed? 12. From the balanced equation. So you can be able to see it's a ratio of 1:2. And then you can be able then to tell that at the end of the day, the number of moles of sodium hydroxide that are required is 12. But the number of moles of sodium hydroxide that are available is 5. Hence, it will not neutralize the sulfuric acid spill. All right, let me just go through this again so that it's guaranteed and people can understand how this thing goes. All right, let's pull this from there on. Follow my lead. Now, let me read the question from scratch so that people can work with me. A learner accidentally spills 15 or 0,4 of sulfuric acid. So visualize it in your head. I spill a certain volume of a certain concentration. To deal with the spillage of an acid, you need to neutralize, so you need a base. He adds 25, that's the volume of the base that he added. 0,2, that's the concentration. And the question then goes on to tell us that the attempt to neutralize is not enough. I'm given the formulas here, and it says, show by calculations that the addition of sodium hydroxide will not neutralize the sulfuric acid spill. So we're supposed to show that you did not put enough of sodium hydroxide to actually neutralize. Hence, I started by calculating moles, which is always my language. My language is moles. Get me moles. How many moles of sodium hydroxide did I spill? 6 by 10 to the power negative 3. I'm taking it from the formula C squared N over V, and I'm making N the subject of the formula. So in terms of how many moles of sodium hydroxide of sulfuric acid that I spilled, it is 6 by 10 to the power negative 3. In terms of the moles of the base that I put to try and neutralize, I put 5. And then I'm saying, okay, you compare ratios to be able to tell how much of the sodium hydroxide you'd actually need. You have 5, that's what you have. According to the ratio, which is 1:2 from the formula, 1:2. If I have 6 moles of sodium of sulfuric acid, if I have 6 by 10 to the power negative 3 moles, I would require X of the sodium hydroxide, which I then found to be 12. Remember, you cross multiply. 1 times X is X, 2 times this is 12. So for every 6 moles of sulfuric acid, I require 12 by 10 to the power negative 3 moles of sodium hydroxide. But I have 5, but I require 12. That's why you're not able to neutralize. So to conclude this as an answer, you would say the number of moles of sodium hydroxide that are needed is equal to 12 by 10 to the power negative 3 moles. But then the number of moles of sodium hydroxide that are available is 5 by 10 to the power negative 3 moles. Hence, then we would say the sodium hydroxide will not be sufficient to neutralize. Sodium hydroxide will not be sufficient to neutralize. Right. Let me see the questions. I'm ready. What is someone saying? When are we doing this when we were doing these calculations ratios, the place we put X as in one as a way where we suggesting that it's a limiting reagent. All right, no. We're not suggesting that. Actually, we're told it's a limiting reagent, right? So we're told, show that sodium hydroxide will not neutralize. It's not enough. Show that it's not enough. So show that it's limited in this case. That's why I said, for every 6 moles of sulfuric acid, how many moles of sodium hydroxide would I actually require? That's what I said. All right. There's more that's coming, more that's even crazier than what we have here. Okay, I'm about to take this out. Let me just get what people are saying in terms of their questions. So you need 2 sodium hydroxide. Maybe what will help, Nefem, is for you to actually ask me verbally. That way I can be able to say, okay, this is what you mean, this is what you mean. Because I'm really struggling with the understanding of part of your questions. When you say, does it mean 2 times? I would need you guys to really tell me. So please do, so I can be able to pull through. Okay, there's a hand. I'm happy. Talk to me. Go ahead.
Hi, sir.
Yes.
My question is, so for you to neutralize the H2SO4, you need twice of NOLH as shown in the balanced equation. And what we have on the scenario, we have 5 times 10 to the power negative 3 moles, which is not enough to neutralize. the acid.
Yes. So what you have in this scenario is that you've got we've got 5 moles, 5 by 10 power negative 3 moles of the sodium hydroxide. But then, according to the ratio, which is 1:2, I would require to have 12 by 10 power negative 3 moles of sodium hydroxide instead of the 5 that I have. Hence, conclusively, we can say sodium hydroxide is not enough to neutralize this.
Oh, okay. Thank you.
All right. Now, somebody's saying, would I always put X on the limiting region? No, you don't. Not all the time. Contextually, in this question, I put the X because I wanted to find out how much of the sodium hydroxide I would actually need in order to neutralize 6 moles of that one. And from what I'm seeing, I definitely need 12, but I've got 5, so it will not suffice. Okay. It will not suffice. All right, I'm taking this out. Let's try another one, something a bit more interesting. It's a good thing you guys are asking questions. If you ask, you will know. If you don't, you will never know. Story, Assam, 2016 Gauteng, Prelim Paper 2, question 10. Write that one down as a title, and then I will start to work on it. All right. A factory accidentally spills sulfuric acid into a nearby river. The fish species in the river cannot survive in water with a pH lower than 5.8. Analysis of the water sample from the river shows that the hydrogen ion concentration is 5.6 by 10 to the power negative 6 moles per decimeter cubed. Show with the aid of a calculation that the fish will not survive in the river. Perfect. So this is a common thing, and this is why it's important to understand this topic. You've got factories which spill dangerous substances into nearby rivers. And this will affect the aquatic life. It will kill them because the fish live in water at certain pHs. So it says it will not survive if the pH is lower than 5.8. Then the question says, show that the fish will not survive, which is a very big environmental disaster. pH is negative log concentration of the H plus ions. We are told that the H plus ions, their concentration is 5.6 by 10 to the power negative 6. We're already told in advance. Then the question says, show that the fish will not survive. And I hear that the answer is 5.25 in terms of pH. And so it's lower than 5.8. So the fish will not survive. So your answer is 3 marks, 1 mark for the formula, 1 mark for the substitution, another mark for the answer. So they will not survive. If it's lower than 5.25, it won't happen. 5.8 rather, it won't happen. And here we are dealing with 5.25. Okay, somebody has a question. You can lift up your hand, and then you'll pop up faster on my screen. But let me try and unmute you. Go ahead, you can talk. I've just unmuted you. Okay. All right, so I can't hear you, so I don't know what's wrong, but let me continue. Okay, somebody just posted a question. Say, since the sulfuric acid doesn't donate 2 protons, it does. It does. Okay, I think I see now where the confusion is. You're thinking I should multiply by 2. No. In this case, I don't, because I'm given the concentration of the hydrogen ion, not the concentration of the acid. Remember, in the other question, you were given the concentration of the acid, the other question. And then to find the concentration of the H plus ions, you multiplied by 2. That's what you did, right? In this case, you are given this already, which is what you need when you're dealing with pH, negative log concentration of H plus. So be careful of what you're given. Very good question that you asked. It is the H plus that you are given. You are not given this. And so on. So that's why at the end of the day, you just put the number as is without considering multiplication by 2, because you're already given the concentration of that particular or of those particular ions. 10.2, we go. A sample of seawater is treated with 500 cubic centimeters of 2.5 mole sodium hydroxide, sharp, to remove the magnesium ions. The reaction that takes place is represented by the balanced equation. 1 mole of magnesium nitrate with 2 moles of sodium hydroxide to give you magnesium hydroxide and sodium nitrate. Perfect. After removal of the precipitate is the solid, right? And I want you to understand that a precipitate is made when 2 aqueous solutions or liquids react. So you've got the magnesium nitrate, please follow my thinking, and the sodium hydroxide reacting, but they are going to form a solid, which is the precipitate. After the removal of the precipitate, the excess, for me, this is the key word to this question. The excess, the extra, the excess sodium hydroxide is titrated with 95 cubic centimeters of 0.2 mole per decimeter cubed sulfuric acid solution. The balanced equation for the reaction is what you see here. So let me get my scenario here. There's 2 things happening. I've got my first reaction. I've got my second reaction. In the second reaction, reaction number 2, I am reacting excess sodium hydroxide. This is extra sodium hydroxide. So something, if it's excess or extra, it means it was used before, but it was not finished. So some of it is left over. That leftover, that excess, is titrated with 95 cubic centimeters of 0.2 sodium sulfuric acid. So the excess is titrated with sulfuric acid of volume this and concentration that. We begin. 10.21. Calculate the number of moles of sodium hydroxide added to the seawater. So if I go to my first part, a sample of seawater is treated with 500 cubic centimeters of 2.5 mole per decimeter cubed sodium hydroxide. And so the number of moles that we added of sodium hydroxide to the seawater, the volume, the concentration. The choice of the equation depends on the information given. Concentration is number of moles over volume. Number of moles is concentration times volume. So the number of moles will be 2.5. That will be the concentration. 500 cubic centimeters changed into cubic deci, 0.5. Your answer for the number of moles is going to be equal to 1.25 moles. So these are the moles of sodium hydroxide added to the seawater. For 6 marks, the next question, which is very interesting. For 6 marks, the next question. I'm ready. We can start. All right. Let me know where there's a struggle. The next one, I'm pulling through. Determine the original mass of magnesium nitrate in the seawater. Determine the original mass of magnesium nitrate in the seawater. Okay, sharp. Now, I want us to think here. You see, in equation 2, I'm reacting excess sodium hydroxide with sulfuric acid. In equation 1, I'm reacting sodium hydroxide with magnesium nitrate. Somebody has a hand. Let me attend to that one very quickly. Go ahead. I'm listening.
Hi, sir. Can you please repeat the whole question from
Which one?
the 10.2? Like, can you read the statement?
The one that says calculate the number of moles of sodium hydroxide.
No, the whole statement from 10.2 that says a sample. I want to understand I don't really understand the statement, the given information.
Okay.
Thank
A
you.
sample of seawater. So visualize. SW is seawater. A sample of seawater is treated with 500 cubic centimeters of a 2.5 mole sodium hydroxide. So what it means, you put sodium hydroxide here together with the seawater. What volume? 0.5. I've divided by 1,000. What concentration? 2.5 moles per decimeter cubed. And the question says, calculate the moles of sodium hydroxide added to the seawater. You've got volume, you've got concentration. You can get moles. Concentration times volume. Concentration is 2.5, volume at 0.5, moles at 1.25. That's what basically is going on here. Is that okay? I think they've muted themselves. Yeah, I think so. But it's fine. I'm hoping that's clear. All right, let me follow through with the rest of the question right there. And then it says, this seawater was reacted with sodium hydroxide so that you can remove the magnesium ions. And we're given the first reaction. This is the seawater. So this is the magnesium nitrate that is inside the seawater. And then this is the sodium hydroxide that you added. And these are the products. Then the question says, after the removal of the precipitate, this one, the excess sodium hydroxide. So it looks like they reacted, right? But then some extra sodium hydroxide, so some extra sodium hydroxide was reacted with sulfuric acid, whose volume is actually 95 by 10 to the power negative 3, and whose concentration is 0.2 moles per decimeter cubed. So the extra sodium hydroxide was reacted with this volume of sulfuric acid and this concentration. The question for 6 marks says, calculate the original mass of magnesium nitrate in seawater. Right. I'm ready now. Let's do chemistry. Now, let me start with the extra because I'm going to work backwards. That's the fastest way to do things. So let me start with what I had as a leftover. You see, I can get the moles of the sulfuric acid that reacted with the leftover. The number of moles of the sulfuric acid is concentration times volume. The concentration is 0,2. The volume is 95 by 10 to the power negative 3. So the number of moles of that particular acid is 0,019 moles. These are the moles of sulfuric acid. But who did they react with? They reacted with the extra sodium hydroxide. So let me get then the number of moles of the sodium hydroxide, because now using ratios from equation 2, I can tell you that sodium hydroxide to sulfuric acid, the ratio is 2:1. So then from here on, I can get the moles of sodium hydroxide, the extra sodium hydroxide, how many moles it had. So sodium hydroxide, we're looking at 0,019. No, that's for sulfuric acid, sorry. 0,019. And this is X. So the X at the end of the day is 0,038 moles. So who are these? These are the number of moles of sodium hydroxide in excess, right? The extra. So I found what extra we had. All right, so do the logic with me. So using the information of sulfuric acid, which reacted with extra sodium hydroxide, I was able to get the number of moles of the sodium hydroxide that actually remained. But then the question is asking us about the original mass of magnesium nitrate. And then I can pick up my story and say, now, if in equation 1, I used some sodium hydroxide, then equation 2, I have left over. How much sodium hydroxide did I use? Now, notice from 10,21, we calculated the number of moles of sodium hydroxide that we had initially, right? Then we used some of the sodium hydroxide, and then some of it was left over. The leftover is 0,038. Let me give a logic. It's like saying in the morning you had 100 rands, and then at the end of the day you are left over with 20 rands. So you must have used 80 rand. So in the morning you had 100. That's the original amount. Time goes on, you use the money, then some of it is left over, you got 20 rand. That means you used 80. So I can get the number of moles of the sodium hydroxide that was used. I can get it. The initial, your 100 rands is 10,21, which is 1,25 moles, minus your 20 rand, the one that you're left with, the excess, which is 0,038. So it looks like I used 1, let me just take this out, 1,212 moles of sodium hydroxide. So in equation 1, in terms of the moles that I used 1,212 moles. In equation 2, in terms of the moles that I used 0,038. If you add what you used and what you have, you go back to what you had, which was in 10,21. All right, I'm building up my story. So I know how much I used here, but remember, I'm looking for the mass of magnesium nitrate. So the information that I have now is of sodium hydroxide, but the information that I require is of magnesium nitrate. And how do they react? Check the formula. So the magnesium nitrate, in terms of how it reacts with sodium hydroxide, the ratio is 1:2. Okay, let me just take this out in case. Yeah, there you are. So the ratio is actually 1:2. 1:2, right? So whose moles do I know? I know I used 1,212, and this is X right here. So I've got 2X, 1,212. Divide everything by 2. I've got 0,606 moles. So these are the moles of magnesium nitrate that was used. And then I'm not looking for the moles used, I'm looking for mass. Mass, one of the most common formulas is, not mass, number of moles is mass over molar mass. So when you do your maths, it means mass is number of moles times molar mass. The number of moles that are used is 0.606. The molar mass of magnesium nitrate. Let me just put a square to just clarify how you'd get it. All right, so there. So periodic table, magnesium nitrate, how would I get it? I would say it's magnesium nitrate. So the magnesium, I think, should be 24. Then the nitrogen and oxygen, that's 14 plus 16 times 3, which is 48. And then this is multiplied by 2. All right. I'm sorry, I'm just putting this a bit too close to each other. Or let me just move this actually. Sorry about that. Just want to show you how you get the molar mass, because sometimes you guys struggle with that. So I've got magnesium nitrate. So how would I do it? The magnesium is 24 plus, in the brackets, you've got nitrogen, which is 14, plus oxygen, which is 16 times 3, since there are 3 of them. Then all this multiplied by the 2. So don't forget there's a 2 on the outside. Eventually, your answer is 148. So the molar mass is 148. So the mass, the original mass, will be 89.69 grams. 6 marks in the exam. That's your original mass of the magnesium nitrate. Talk to me, fam. Let me hear the questions, see what people are saying as we are working together. We've already passed our first hour, so we're gliding to the last parts of our lesson. Still a couple of minutes left, but we are gliding there. Talk to me. Talk to me. Somebody says, say in acids and bases, do we always write the answer in its original form, or we round off to the nearest number? My suggestion would be just rather round off at the end. But I want you to know that it's not really a train smash, as long as you keep rounding off to 2 decimal places. But I prefer that you round off at the end. I'm not really calculating these numbers. I already did this before. So just run through it from that perspective. All right. This I'm taking out. Someone says, say, is it always the case to first find the moles in excess before you find the mass? Yes, yes. You find what is left over, and you work backwards. You find what is left over, then get what is used, then get what you have originally. So you find out, I've got 20 Rand. How much did you use? 80 Rand. How much did you have? 100 Rands. All right. Okay, let me repeat. Someone says, say, please repeat what you said to, all right. Say, is it always the case? The question was, say, is it always the case to find the moles in excess before we can find the mass? Yes. Work backwards. Work from equation 2. Sometimes I can put 3 equations. Work backwards. Get what you have. Get what you have left, then get what you used, then you will get what you had, right? So usually most of the time they'll give you what you had in the beginning, then you can calculate what you have left over, and then that will help you. The difference between what you had, right, or rather what you had in the beginning, the difference between the 100 rands and the 20 rand left over will give you 80 rand, which is what you used. I'm ready for my next one. More interesting question. Taking this out. Let's give it a bit of some time. You can even take screenshots. It's faster. But I actually prefer also that you write. It becomes easier when you're writing because you can always relate, you know. All right, fam, another 10 more seconds. Acids and bases. What a topic, man. What a topic. Yo. And it's going to be quite a number of marks. I think sometimes it gets to about 29 marks. Imagine. 29 in the final exam. I can't afford to lose it. Can't afford. Gone, gone. And most of the time, it's the calculation that comes through. Somebody says, how did I find the molar mass? I did show people how I did, but let me just give it a boundary on where I did it. That 148. Is it 148? You can confirm with me. But I think it is 148. I did put a bound. This is the one that I used right there. Your calculator is saying 1,488. Oh, no, it can't. That is crazy. That'll be too high. That's a crazy number. I just try it. Are you guys getting the same thing? Oh, it's 1,488. Yes. Guys, I think it's 148. It is. It should be. It is. All this from the periodic table. All right. I'm ready. Out, gone. Thank you. Next question. Here we go. So we start with simple definitions, 2019 Limpopo. Write down. We start with simple definitions, then we're going to up our game in a calculation. Simple definitions, then up the game. So just to get you guys excited, can you please do these ones? I'll give you 4 minutes. At least now I try, Chuck Norris, ne? Try, right? Try. 3 minutes is fine. 3 minutes. Go. Then I'll do the calculation. Samintwana. All right, here we go. Sulfuric acid is a diprotic acid which is used in the industry. Define an acid in terms of the Laurie Bronsted. I know you said a proton donor. Thank you. Then it says, give a reason why sulfuric acid is referred to as a diprotic, because it donates 2 protons per molecule of acid, donates 2 protons per molecule of acid. Then give a reason why it's regarded as a strong acid, because it ionizes completely in solution to form a high concentration of hydronium ions. If you don't say that, it's not complete. Ionizes completely in solution to form a high concentration of hydronium. All right. Then here, okay, somebody raise their hand. Just go ahead.
For 7.1.3, is it wrong if I said no? 7.1.2, my bad. Is it wrong if I said it is able to donate 2 H+ ions, not proton?
It's fine. It's okay. 2 H+ ions, that's a proton. It's fine. Per molecule. You must say that per molecule.
Yes.
All right.
Okay,
It's
thank
fine.
you.
Perfect. 7.14. 7.14. Okay, let me see if, yeah, it's fine. All right. 7.14. Write down the name or formula of the conjugated base of sulfuric acid. Conjugated base of sulfuric acid. So look at this. You see, when an acid donates a proton, right? And because it's diprotic, it will donate 2 protons. It forms a conjugate base, and this is the conjugate base. They said name or formula. So let me just clarify something, 2 minus here. Whenever you lose, you become negative. If you lose, you become negative, right? And if you have lost 2, you become negative twice, 2 minus. That's why it's SO4, 2 minus. Maybe the topic electrochemistry would make this a bit better. So this is the sulfate ion. I actually saw a question where they were asking the name. So the name, I'm writing it down, sulfate ion. That'll be the name, sulfate ion. So the formula will be SO4 2 minus. Remember, every time an acid donates, it becomes a conjugate base. 7.15. What is the common name given to a substance which can act both as an acid or a base? I know you got it. Ampholyte. You said it's an ampholyte. Ampholyte or amphoteric substance. Ampholyte. All right. Ampholyte or amphoteric substance. The big boy. Calculation. So, 7 marks. Story. But before I do the story, I like to make an illustration so that you can understand how this would work for 7 marks. Now, when you've got a container right there, and you put a substance of a certain volume and a certain concentration. So this is my substance, certain volume, certain concentration. So let me call the volume of this substance V1. Let me call the concentration of this substance C1. When you want to change the concentration, you need to add water. So I'm adding water now. I'm adding water. So which means now I will have a different concentration, which is C2, and also a different volume, which is V2. So the C1, V1 are my initial concentrations, volumes of this typical substance, right? And then C2 and V2 are the concentrations and volumes when you have added the water, right? When you've added the water. Now, in this case, I want you to understand that the C1, V1 multiplied together is actually equal to C2, V2. And this is an important formula when it comes to dilution. This is a thing that you do every day in the house, every single day. That's what you do. When you are drinking oros, here's your glass. What you do, you put a certain amount of oros, certain volume of oros, certain concentration of oros. That's your V1 oros, C1 oros, original oros. You dilute it with water to the desired concentration or sweetness, for lack of a better word. And now you've got a new volume, V2, a new concentration, C2. All right? So that's what you have. And C1, V1, and C2, V2 are always equal. Very important formula to remember when it comes to issues to dilution. If you check my handouts, I do have this formula. I put it in detail. I explained everything properly. Now, having said and laid down the background, let's start our story. 7.2 for 7 marks. Here we begin. A lab technician wants to determine the concentration of a hydrochloric acid sample. Okay. He adds 10 cubic centimeters of the hydrochloric acid sample to 490 of distilled water to give 500 of dilute hydrochloric acid. Let's have him visualize. What did this guy do? He added 10 cubic centimeters of HCl. So the volume V1 originally is just 10 cubic centimeters. So this is your 10 cubic centimeters. Okay, sharp. And what did he do? He added water. How much water? 490. Now, when you add 490 of water and 10 of the acid, right, you're going to have 500 of the solution. So the V2, the new volume, is 500, which is like, let me write this 500, it's fine. It's 500 cubic centimeters, 490 of the water and 10 of the HCl. Then it goes further. During a reaction, 100 cubic centimeters of this HCl solution. So here the total solution is 500. Then we're told that 100 cubic centimeters of this HCl, so they took out 100, reacts completely with 0.32 grams of sodium carbonate. Okay, so let's look at the idea. They tried to put the diagram to make our lives easy. So this was your original HCl. How much did you take from it? It's like a bottle of Oros, 9. How much did you take from the bottle? I took 10. Where did you put it? In 490 of water, which makes it into 500. What else did you do? From that solution of 500, I took 100 and reacted it with 0.32 grams of sodium carbonate. That's what I'm learning. Okay. Then it says the balanced equation for the reaction is sodium carbonate plus the hydrochloric acid, sodium chloride, carbon dioxide, and water. For 7 marks, calculate the concentration of the original HCl sample. Calculate the concentration of this sample. Calculate C1. That's what we're looking for. C1. Okay. Right? Are we still together? Hopefully people are. Here's my story. C1, the original concentration, what I'm looking for. What do I know? Now, I know that 0.32 grams of sodium carbonate reacted with 100 cubic centimeters of my HCl, the one that I took from the dilute there. My language is moles. Let me get moles. Let me get the number of moles of sodium carbonate, which is mass over molar mass. So the mass is 0.32. The molar mass of sodium carbonate is actually, sodium is 23 times 2, 46, plus the 12, plus oxygen. You get a hang of this, right? Which gives you a number that is 106. So in terms of the number of moles, it's going to be 0.003 moles. These are the moles of sodium carbonate that are reacting with this hydrochloric acid, whose volume is 100, that I took from the dilute solution. So let me get the number of moles of the hydrochloric acid that is reacting with this number of moles of sodium or carbonate. So if I think about it now, I'll say to myself, the sodium carbonate right there, the hydrochloric acid, the ratio is 1:2. I know the moles of sodium carbonate, it's 0.003 moles. And then the ones for HCl, I'll just put it as like this. So X is equal to 0.006. So I cross multiplied. Okay, sharp. So these are the moles of the HCl. I'm talking about moles here of the HCl. And it's, work with me. Where did I get this HCl from? I got it from here. How much volume did I take? 100, right? So then I can get the concentration of this HCl in 100. I can get the concentration of the dilute HCl, which I took from here, because when I take 100, it's dilute. So then I say to myself, the concentration of the dilute, which is C2, right, is number of moles over volume. So the number of moles is 0.006, and the volume that I put here was 100, which is 0.1 cubic decimeters. So the concentration of the dilute is actually 0.06 moles per decimeter cubed. But the question says, calculate the concentration of the original HCl. All right, what are people saying? How did we get 0.03? It's the number of moles, the mass. Okay, stop the bus. Oh, Tico, I stopped the bus, Shem. I am stopping the bus. I'm stopping the bus. Right. What is the questions? Or what are the questions? What's going on? Yo, you guys crack me. All right, let me reiterate this. All right. So I'm here. I'm actually here. What is here? 0.32 grams of sodium carbonate. So I got the moles of it. Mass over molar mass. 0.03. And it's 0.003. That's what I got. These are the moles of sodium carbonate that are reacting. Okay, guys, are we not getting is the answer not 0.03? Is that, what is the answer? What is 0.32 divided by 106? Let me check. 0.32. I'm actually taking this from the memo, so I didn't want to waste time calculating. Maybe it's wrong. Yeah, there. 0.03. What is the problem? Ivo, stop the bus. Stop the bus. Where are we going? You guys crack me. Okay, I got your back. That's why you're here, man. Let's do this. Let's do this. So let's take it step by step, and where you don't get it, we'll work together. All right. And so we'll take it up from there. Right. What is it that you don't get? What is it that you get? So let me just keep continuing. You will tell me where you are winning with this or where you're not winning. So the 0.03 is proper, is at the number of moles of the sodium carbonate. That's okay. Right. And then this sodium carbonate is reacting with hydrochloric acid. Ne? The hydrochloric acid is has a volume of 100 cubic centimeters. And it comes from here where it was 500. It's like saying from the 500, when you only took 100 to react with sodium carbonate. That's what you did. And so Minalana, what I have is the moles of sodium carbonate. That's what I have right here. The moles of sodium carbonate. And then from here on, I want to find the moles of hydrochloric acid that is reacting with this moles of sodium carbonate. And I just do the ratio 1:2 from the balanced equation. 1 mole of this, 2 moles of that. And then I do that ratio. Then from that ratio, I get the moles of sodium, of hydrochloric acid that is reacting with sodium carbonate. So here, in terms of the language, I'm reacting 0.03 moles of sodium carbonate with 0.06 moles of hydrochloric acid. Where did I get this hydrochloric acid from? From here. How much of it did I use? 100. So the volume that's inside here is 100, and the moles that's inside here is 0.06. And this volume, this 100, is from 500, which was dilute. And from that 500, I took 100. I took 100 from that 500. And I'm saying in that 100, I have moles of 0.06. I have 0.006. I have volume of 0.1. So I can get the concentration. And remember, I'm saying it's C2 because it's the dilute one. The concentrated one, C1, is here, which is what I'm looking for. So C2 is 0.06. So that's the concentration of the diluted substance. But I'm looking for C1. All right, the bus has been stopped. Talk to me. Talk to me. Where are we? What are I? Somebody says, say, can we use C squared M over MV, then use the titration formula to get the concentration of ACl? We can't, because we don't have the volume of the solution of sodium carbonate with hydrochloric acid. You only have 100 cubic centimeters. And you must take in respect that adding water, or adding the 100 cubic centimeters into the sodium carbonate will increase the volume. It's like adding water to a place where there's stones, like maybe there's a container and there's a stone in it. You add water, it rises that water level. So the volume must be considered to be more than 100 if you're dealing with the 0.32. So you can't do that. You can't. You need to do them individually as moles, then compare the ratios. Let me just get the series of questions, right? The bus can go now. So say, will the 0.06 be for the 500? Yes. Much as it's for the 100, it will be for the 500 as well. All right. So then I now know, because I took the 100 from the 500 to begin with. So what doesn't change is the concentration. What is changing is the volume. That's all. But the concentration remains pretty much the same. And so I've got the C2 now. And I'm looking for C1. All right, let's continue with the bus. C1, okay, there's another question before I go. Oh, okay, it says I understand. C1 V1 is equal to C2 V2. And I'm looking for C1. Who is C1? C1, I don't know. V1, the original volume was 10. That's what they told us. So it is times 10 by 10 to the power negative 3. C2, the one which is dilute, 0.06. V2, remember the volume where it was diluted, it was 500, right, which is 0.5. Right there, it was diluted to 500. And I mean, I'm looking for C1. So the rest is met, 0.06 times 0.5 over 10 times 10 to the power negative 3. The original concentration for 7 marks was 3 moles per decimeter cubed. Talk to me. Yay. All right. So I think there's another question that comes through. I still struggle to know when to use C1V1. Just a brief explanation when to you use it when you have a situation where you've got a concentrated substance that is eventually diluted by adding water. That's where you'd use it. Concentrated substance that's eventually diluted to add water. And by adding water. So C1, V1, C2, V2. That's when you'd use it. So those questions will quite be clear. They will tell you that a certain substance has a concentration of this, a volume of this, water was added, blah, blah. So you'll be asked to calculate about C1, sometimes about V1, sometimes about C2, sometimes about V2. It's just a matter of understanding which is your scenario. Right, there's another question there. Oh, I understand. Say, what's the reason behind using the volume of 0.5? This is because when you diluted originally to 0.5. That's what you diluted there, right? So you diluted to 0.5. That's 500 cubic centimeters. And you took a sample of 100. I can't be using 100. I can't put 100 here because that's not the V2. V2 is 500 there. That was my dilution volume, V2, right? And so that's how we have it. So say for concentrate, we use C1, V1, C divided by CP, VB. No. You use that in titration. CA, VA divided by CB, VB is for titration. This is not a titration, not necessarily a titration, right? You're just seeing C1, V1, C2, V2. So for titration, that's what you use. And again, fam, I don't want you to memorize Wuti. When I'm here, I use this. I mean, I want you to be able to do these questions to an extent that you can actually be able to tell just by looking at, okay, this one, I can use moles, I can use volume, I can use what. Yeah, one. So I don't want you to memorize because the questions can come in very tricky ways. And I'm encouraging you guys to actually watch my other video on acids and bases, actually on my YouTube channel, my other 2-hour video. I was doing different questions from this. And you have this one as well. So you have 4 hours of free acids and bases, different questions, different ways of thinking, so that at least the more you do, the more you know. That's what Mr. X offers for free. That's the free things that you are loving, that you are always looking for all the time. That's the God bless you, Mr. X free things. Those kind of things. They're there, Dwan. They're there. Don't be afraid. They're there. So you'll do more by watching more. Okay, there's a question that came through. Let me just get this right. Please repeat the part about C1, V1. Okay, maybe let me just get what you don't understand so I can know how to answer. I can't answer without knowing what the problem is. So let me try and unmute you. Go ahead, I am listening. Somebody says forever, free things, never. Yo guys, I don't eat free things, ne? Free things don't pay me. I'm just doing this because I actually like you. And I actually want you to pass. It's after hours, it's after 9. You can hear my voice. It's tired. It's been a long day. I take hours to prepare these handouts, all these things, all that. So I think the least we can do is just basically to be just grateful and also to pass. Yo, that's the reason why we're doing this after all. Say, how did you get 10 by 10 power negative 3? That's this V1. There. He adds 10 cubic centimeters. You multiply that by 10 to the power negative 3 to actually get your cubic decimeters. That's why. Change volume from cubic centi to cubic deci. All right, I'm trying to unmute the person that's interested in the issues to do with EC1, V1. All right. Okay. Let me see what I can do. Actually, I'm not getting through to that person. So, hey, Buffett, I don't know what's going on now. What can I do? All right. In this case, the basic idea was just to go backwards, and in most cases, just work backwards and be able to come through and get your C1V1 is equal to C2V2. All right, fam. Having said that, I think this would suffice to be our last question of the day, looking at our time. And I want to just talk about how, okay, somebody's raised their hand. The one who I tried to unmute. Go ahead. Let me just have you. Your question will help others as I'm answering it. Go ahead.
Hi, so can you hear me?
Yes.
Oh, my question was about, like, I don't know, I still struggle about the equation C1V1 is equals to C2V2. Can you please explain again on how to use it?
Oros. Start with oros. That's the best way. This is what you do when you're in the kitchen. Glass, oros. What did you put here? Oros. A certain volume of oros. A certain concentration of oros. That's what you put there. In it, add water.
Yes.
Add water. You got a new volume now, a bigger volume now. That volume is V2. And add water, you've diluted. So you got a new concentration, C2. And I'm saying C1, V1, if you multiply them, they're always going to be equal to C2, V2. You use this formula when dealing with moving from concentrated to dilute and vice versa. That's where you use the formula. So in this case, this was your oros, C1. And from that oros, your original bottle of oros, from that oros, you took 10 cubic centimeters, right? That's your V1. You took 10. And then you don't know the C1. Then in that particular 10, you added 490 of water to make it to 500. That's your V2, 500. Then once you've got that 500 volume, you take 100 of it, put it inside here, and it reacts with 0.32 grams of sodium carbonate. Then eventually, you're going to get to a point where you can calculate C2, work backwards, and then get your C1 again from scratch. There is a question that I think I have on my other video where I was addressing this. You can try and watch it. Maybe you'll be able to understand more. But the intention is to make sure that you get there. All right.
Okay.
You're welcome on that one. Okay. I'll appreciate your comments that you guys are putting through. Thank you so much. This is much appreciated. Having said that, family members, we've come to the end of our lesson, but let me give you just a couple of announcements to just end our session nicely right there. All right. So here's what I need you guys to remember. First up, if you practice more, you will know more. You practice less, you will know less. And one of the best things to do for yourself this year is to attend my classes for the typical Mr. X revision classes. Or if you want, you can attend those small ones that are the group classes that are happening on a typical Thursday and Sunday. You can contact me. You can be able to know quite a lot from there on. Then this one here is the Mr. X Massive 3-Day Revision, which is going to be taking place on the 31st to the 2nd of November. That's for mathematics. Then 7th to the 9th of November. That's for physical sciences, 3 days, 8 hours a day. And it's going to be 1,000 rands. So you can register or book, and it's for free when you are booking. So you don't need to worry about that. Game changer. I tell you this, you don't want to miss this. Now, on a lighter one day, you're going to be having these ones here during the week. So tomorrow, analytical geometry, electric circuits, which is a crazy topic that you struggle with. Yo, you should see the way I teach it online. Got the diagrams, the dynamics, and everything. It's crazy, man. Electric circuits, part 1. Then on Sunday, analytical geometry, we're going to run through that one there. So please do attend those lessons so that you can get through. But these are not free. It's 100 Rand. Free, the one that you love with all of your heart, is the one that we've just done now. But notice that I want to have free things all the time, people. All the time. I will not have that. Thank you so much for everything. From my side as Ukolani, I appreciate you. Thank you. God bless you. I love the messages that you're sending. You really appreciate. Yeah, Hambi Pasi, Oros, and all. I really, really will do more for you guys as we go on along right there. Thank you. Take care. I'll send the recording. Not even send it. I will upload it on my YouTube channel. I think tomorrow, because I want to sleep now. I'll upload it on my YouTube channel tomorrow, and then you guys can take it up from there. Take care and good night.